So the next talk will be, so next speaker will be Sajid Hussain, and the topic is Magnetoelectric spin orbit memory concept and future challenges. Dr. Sajid Hussain is a senior postdoctoral researcher at Lawrence Berkeley National Laboratory. He has obtained his PhD degree from Indian Institute of Technology, Delhi, India. Before joining at Berkeley, he has conducted research at the laboratory Albert Fer CNRS Thales in France and Uppsala University in Sweden. His research interests are in electrical control of magnetism in multiferroics, multiferromagnetic spintronics, quantum materials, and magnonics. He is leading the group at Ramesh's lab, and his current research focuses on the electrical control of antiferromagnets, aiming to advance magnetoelectric spin orbit memory and logic functionalities. Okay, Sajid, you're welcome to start the presentation, and you'll have 25 minutes.
Thanks, Peter, for the kind introduction. Just a second. Yeah, thanks, Peter, again. And thanks for joining my talk. And thanks to organizing committee for the invitation. So, okay, so I will talk about more kind of a, maybe my talk is involved kind of a tutorial for students and for some expert. So my talk will involve more on the energy part than the physics. So did you know that more data has been created in the last couple of years than the entire human history? And this will basically pose a lot of challenges on the existence of our energy. So in my talk, in the next 20 to 30 minutes, basically, I will going to talk about more on the key factor that will change the way we think about the innovations. And yeah, this involved a lot of collaborators and my group members, and I would like to thank everybody to basically to support and work in this work in my research. So this is my basically the outline of my talk. So as I said, I will mainly focus on the key role of the energy in computation, and I will discuss more of how we can invent the new methods and new approaches to tackle this problem. And I will focus on in my talk is multiferroics based memory computation, and of course the new concept that generated in my group and with Intel a few years back, that's called MISO. And of course I will present my some of my data, and of course at the end I will present some pathway to enable such kind of memory storage. Okay, that was the beginning line of my talk, that the energy storage is like these days, as of you can see in the graph, that is going exponentially higher. That's the basically decadal plan from the semiconductor company, that in 2030, that's up to 2030, and after that is gonna saturate, because your world energy production is limited, and in 2030 you're basically gonna use like a 20 to 25% or even more in microelectronics, and that's a big problem. So even you reduce the energy, the device size, or so many things, but you are limited to the instruction per second, because the instruction per second is limited by the energy. So every instruction you're putting into the computer, it is consuming some of energy, and that is the main thing. Whether you are reducing the size enough or increasing per terabyte per inch square, it doesn't matter. But the energy is the main killing factor here. So that's my focus is on that, mainly that how do we tackle this problem. And of course, we need a fundamental paradigm shift, actually. So this slide is more on tutorial. I don't know why it is stuck here. Okay, so in every basically computation instruction, or any memory storage or any bit, you perform operation from 1 to 0 bit, one state to other state. Basically, it involves it has some barrier in the two state, and that's basically consume some energy, and that energy process basically defined in terms of like a change in entropy in your system, and that's simple kb log omega, which is omega is a degree of freedom of your system. That's some spin and charge, and in some non-interacting system, which are semiconductors, all they have a 2 to the power n number of degree of freedom, but there are some other system which are basically the correlated system. In this system, which are non-interacting and uncorrelated, the energy, if you calculate the total energy, it goes n-kBt log 2. So n is the factor, which is the number of degree of freedom. And if some other system you choose, some correlated, highly correlated system where your n is equal to, because all the electrons are, all the constituents are correlated, and they are highly correlated, so that you can basically consider it as a one entity. And if you calculate this energy, it basically goes to kBt log 2. And it means that you have a space that you can reduce the energy consumption by using such materials. So in my talk, I will focus on some kind of a highly correlated material involvement in new kind of device. So we are looking for alternative to what CMOS works. So CMOS work on semiconductors and so many other things. But we're looking for some approach that we can, if we can change some a memory architecture into a different regime, and that's basically the goal, is to reduce the consumption to 1 autojoule per switch, and that's like a minus 18 joule, and it should be non-volatile, of course. So my proposal is here is if we use some material and calculate the energy, and basically it's a 2 of P into VC, which is like a random number here. I should not introduce this way, but P is the polarization of the material, electrical polarization of the material, and VC is a switching field, a switching voltage. And if you basically multiply these two, and you end up with a number which is like an autojoule range. So if you compare with the existing technology on spin-based and some others technology, that you will end up this star. Basically, this number goes very low in autojoule range. And based on this process, Intel and my group, basically Professor Ramesh in 2019, they developed a new concept based on a magnetoelectric material. We call it meso. So it's called a meso magnetoelectric spin orbit logic. I will just explain in a bit. So this is material which I am calling is a magnetoelectric. In magnetoelectric means you can control your material or your system by magnetic field and electric fields, both. So basically, it's a combination of a ferroelectric and ferromagnetism. So you can control your material, your order parameter using electric and magnetic field. I'll show you how it works. So this is a concept, as my title says. So meso concept means you have some magnetoelectric material coupled with spin orbit material. So here, let me just bring my laser pointer. Okay. So this is a one, let's say 1 bit. Is a whole is 1 bit, and the other one is a second bit. So using the input current or input voltage, you control this magnetoelectric material. And this magnetoelectric material is coupled with a ferromagnet. So magnetoelectric is basically it's an antiferromagnet. And antiferromagnetism, basically, I think I believe that people are aware of this. Antiferromagnet and ferromagnet, they are basically coupled through the exchange interaction, and you can use this exchange coupling to manipulate your magnetic material in red through the blue, which is a magnetoelectric material. So electrically, you are able to control the magnetic material. And then in a second step, this magnetic material is aligned in particular direction, and you can use a supply current to polarize this spins. And then back, you can convert through the spin orbit coupling material by inverse spin Hall effect. You can convert back into the charge. So in this process, you are using some charge current and output as a charge, but M is working as a memory bit. So at output, will go into the second bit, and you can control this. That's a electrical engineering work. So I'm not going to into that how to control, but we can control the input of the second bit by the output of the first bit. So that's the working principle of this meso. It's a little bit complicated, but yes, this is the way. So that's the recent experiment done by Felix Casanova and Manu Lubes and Ramesh, my group. So that's the one that I was talking about, the electrical control of the magnet. The hysteresis on the right is basically the output voltage coming out from the interaction between the bismuth ferrite is a magnetoelectric material and the cobalt iron, and that's X voltage is coming basically is an electric field going into the bismuth ferrite, and the output is basically the spin charge conversion from cobalt iron to platinum, and this peak to peak number is telling that you can switch the magnetic material or magnetization of cobalt iron using bismuth ferrite, and it's about like a 500 to 600 millivolt. And I mentioned in my previous slide that's 100 millivolt we need to go to reduce the energy of the order of 10 power minus 18 joule. But this device has some issues, and this issue basically is limited by the spin polarization of ferromagnet, because as I said, we need 100 millivolt output. But here it's if you calculate this back into the voltage, this is basically kind of a 100 of microvolt. So it's like still we need a 3 order of magnitude enhancement and high error rate, because your BFO is connected with cobalt iron. So you have sometime you miss the switching of cobalt iron by switching the magnetization or antiferromagnetic vector in BFO using electric field. So it's a high error rate and a limited polarization by the ferromagnet. So then I entered into this field to simplify this structure further. And what I did here, actually what we did here as a group, is we removed everything. We use a magnetoelectric material in the middle, and we use a spin orbit coupling material on the other side. So we're not using any more ferromagnet. What we're doing, we are trying to play with the bismuth ferrite as a magnetic medium to increase the output voltage, or to bring this system into the real world. And to more simplification, we just using material, and we just using this whole device as a non-local magnon transport device, conventional magnon transport device. So this is a bismuth ferrite magnetoelectric material, and we put some of SO electrode on top of it. This is our first demonstration years back for my colleague, that this is the electrical hysteresis, and it's exactly overlapping the hysteresis, which is measured as a function of electric field in this device, the open circuit voltage. So open circuit voltage means whatever you're measuring here, that's the influence of the magnetoelectric material and the spin Hall effect. So basically you are exciting the magnons in bismuth ferrite, and you're measuring the voltage output as an open circuit voltage. So it's following exactly the polar order. So this is the polar order, and this is the magnetic order. And I will use a lot of stuff similar to that in my following slides. So let's go a little bit of magnetoelectric material. I skip a little bit because I'm very slow in my talk, but yes, I will take care of that time probably. So that's the magnetoelectric material I'm talking about. So it's a little bit of complicated structure, but this is the bismuth ferrite structure. You have a M1, M2. So this is like a one lattice of bismuth ferrite, and the structure is like if you see my hand, it's like elongated and in some direction, and that's like a direction of my polar order. And you have an iron in the center, you have bismuth on the corners, and oxygen in yellow. So using two nearby unit cell, we can basically explain the M1 and M2 coupled antiferromagnetically, and using because of the DMI, because of the structural inversion asymmetry in the material and the polar order. So it has some spin ordering of 65 nanometer here on the right. Here on the right, in the red and blue, they are all two antiferromagnet, couple antiferromagnet, but because of the DMI, they are not completely parallel. If you see my hand, they are a little bit tilted a few degree angle in the in plane, and that give you some canted movement. And you can measure this canted movement using NV magnetometry. I will explain a little bit of that. So these are ferroelectric domains using piezo first microscopy. There are magnetic domains. These are spin cycloid, we call it. Okay, so that's about the bismuth ferrite. It's a little bit of more theory, but I will touch a little bit of that. So this is all energetics of the bismuth ferrite, bismuth strain, exchange interaction, and blah blah blah. But yeah, the last two terms are important one, which represents the polar order, the last term, and the second last is basically the octahedral tail between the two unit cell, like here and here, omega term. Okay, so these two are important. So we can manipulate these two terms by using some external influences like doping and changing the lattice and strain and so many things. And this is the one I was talking about, that we can use some sensitive tool to image the magnetic domains. And these magnetic domains are very small. So because the magnetic movement of the bismuth ferrite is 0.045 Bohr magnetic performance, which is very small. And we need very sensitive technique. This is NV micrometry. I think I don't want to go into the detail, but yes, we can do a clean imaging of such structure. So these are two images on the left and right. Left is, as I said, we can control these magnetic domains using different ways, like strain. So on DSO, is dysprosium scanded substrate, we can have a nice stripes. And when we grow on strontium titanate substrate in different orientation, we see the Turing pattern. Turing pattern is some kind of a theoretical concept. It's like a different pattern formation, natural formation in the materials. So yeah, we can control these architectures using the materials engineering. Okay, so some of a spin orbit coupling, because this is, like, as I said, because we need to enhance our output. So we are doing a lot of other external engineering to improve the system to make it working as we propose as an to get 100 millivolt output. And now spin orbit coupling is again important part to understand. And I think I don't want to go into the detail, but it's like simple spin orbit coupling material is like you can polarize your current using such material, and intrinsically the Barry curvature is basically very important to play with. And if you try to basically clean up your material in a good way, you can enhance this effect a lot. And similarly, like the platinum as a let's say Fermi level, you have a larger spin Hall effect. But even gold is a heavy metal, but it's not, because your Fermi level is shifted downward. So if you can play with that, and you have like low range of materials to play with, and you can have like a larger spin Hall angle. And some oxide material, we recently proposed that these materials are very important to demonstrate such kind of a high spin orbit coupling and high spin Hall angle. So that's the purpose, to understand this spin orbit coupling material, if they can work better way to increase our output, because magnetoelectric material and spin orbit coupling material both are important for us. So the method that I'm going to explain, as I mentioned earlier, that it's a non-local method in the beginning. I will try to show you some data. So we can have we have two methods to measure our output voltage. First is a spin Hall effect driven. So in one of the electrode, you supply some current, and because of the spin orbit coupling, spin charges to spin conversion, you have polarized current here. And because of the spin accumulation, you transfer the angular momentum to the magnet here, and they travel in the whole material, and you can pick up as an inverse spin Hall effect voltage and the output. And it's a first order effect, and it's a second order effect. You basically measuring the heating, heated excited magnons in the material. So I will bring this word magnons in antiferromagnetic. So because bismuth ferrite is an antiferromagnetic, as I showed that in my previous slide, the cycloid is antiferromagnetic cycloid, but we can excite through the spin Hall effect and through the heating effect, and we can measure the output voltage. And I'll show you how. So the magnons are basically the coherent excitation, simple. I don't want to go into that. So that's our experimental geometry in the first. We supply some current and the spin orbit coupling material, and we measure output voltage. And there's another terminal here, is E, which is electric field. we are applying simple voltage. We are scanning the simple voltage in our device and trying to see this effect as a constant current as a function of electric field. So there are, to check the sanity check our whether this experiment is working or not, we did some tests like between platinum, tungsten, and strontium iridate. So platinum is a spin Hall angle of 3%, and tungsten is larger, and strontium iridate we predict to be larger than 1. So the blue is a tungsten, and black is a platinum, and they are opposites. So it means that your sign of the spin charge conversion is changing by changing the platinum to tungsten, which means effects are real. And of course, as a function of SOC and a power, you see that the difference is large. Tungsten to platinum to tungsten to the strontium iridate, the SiO. And then the electric field scan, the red is a polar hysteresis. It's a polarization in the material hysteresis. And then blue is the output voltage as a function of electric, which basically overlapping each other. It means that we can control the magnetization or antiferromagnetism, antiferromagnetism using electric field. And this is some imaging. So if you closely look into that, these stripes going this way to this way, when we change the electric field direction, it means that your antiferromagnetic cycloids, the domains are changing as a function of electric field. And of course, that's the output is real and increasing with the spin orbit coupling material. That's the most interesting. I will end with it, but still I have a lot of stuff to speak. But this is like a conclusive graph. I will bring you this again in my end of the talk, but this as a function of spacing. So see the 100 milli-electron volt, which is our target. And when we reduce the spacing between the two electrodes, basically you increase the output. So you have several ways to play with that. And this is our target. Of course, the future challenges are to change the scheme of the measurement, the fabrication, and the materials. You can play with that output voltage. And one of these legs, basically, we are going to play with the material aspect. So when we in this whole slide is the idea is to manipulate the multiferroic material by using the doping or changing the height of our energy landscape. And of course, the strain, if you free your material from the strain or from the substrate, if you basically a freestanding material, you reduce the coercive field significantly. And of course, the coercive field, even we reach to the 200 millivolt, and that's what our target is, 100 millivolt. So one of the treatment I did is we doped with the lanthanum and bismuth ferrite, and what we see here, the vector, the green or color vectors are basically changed a little bit, and this change from the theory, folks, we asked to calculate the energy. So in lanthanum .BFO has a lower energy switching, and then BFO. So and magnetic domains are also different. So these are BFO on the top right and bottom right is basically the lanthanum BFO. So you have a multi-domain system now. But what we did some experiment by putting a lot of electrodes on a sample, and the same experiment, second harmonic, same data again, electric field scan as a function of the voltage output. What we see is basically after electrical polling, these are my platinum electrodes here. What we see in the middle of these two is a single domain, and that's the one we were looking for. And if you compare with bismuth ferrite and lanthanum bismuth ferrite, the output voltage is significantly higher, which was our main target to play with. And that works actually. We imagine a different way using some other technique, and it's a single domain. And now the magnetic domain is a single variant now. If in the previous you see the multi-domain system and canted movement, now it's a single variant. So it means our magnons are not scattering anymore. Basically, they are going basically they're not losing memory anymore. They are losing less memory, and then you can have a larger output voltage. And it's very stable. So that's the idea. So it's very stable. P up, P down means we apply electric field, remove the electric field, and measure the output voltage for thousands of seconds. And this is the retention. So it's basically you can use this system as a non-volatile memory. So you can switch the P state and leave it there, and you will get the same state after a longer time. That's the idea. And the final idea is like because as I mentioned, this was like idea was to get a vertical device, but it's like not so easy. So a lot of intense fabrication and growth process involved in that, but we made it. And now the output voltage about a millivolt. So in the same geometry, we use the current here or current here, and we measure the voltage output. And it's a magnetization changing using the electric field. And P up means like you have a voltage plus voltage or plus electric field to minus electric field, and you basically can manipulate your stuff using electric field. And about a millivolt. Now the output is about a millivolt. So the final slide is basically it's a benchmarking. It's a kind of second last slide. It's a benchmarking pathway. So these are conventional system, and these are correlated materials, which I showed you earlier. And now the proposal is to confine the magnon, because if you confine the magnons, basically you basically are not losing a lot of information, not so much scattering. That's the idea I'm working on. So the ultimate goal is to go to 100 millivolts. So yeah, so the opportunity how to use such material is to make it cleaner and cleaner, and to use the intrinsic intrinsic property of the material. These are some listed things that you can think of how to how to play with the material and what you can do to increase your output. And that, as I mentioned in the beginning, that to reduce the energy of the consumption in the switching, you basically have to reduce switching voltage and the output voltage for our if you think in terms of changing the landscape of the material and so many things. So thanks you for your kind of attention, and yeah, I'll look forward to the questions. I'm at time. Thank you.
Yeah, thank you very much for the very good presentation. So the talk is open to questions. Are there any questions from the audience? If there are no questions from the audience, I will ask some quick questions. So questions I have, they're related to some technical parameters of devices that you described. For example, when you're switching, what is the switching time?
The switching time in multiferroics, you mean the voltage switching?
Well, the switching from one state to another, because on slides.
Oh yeah. That's right. Okay. So that this is limited by the set of instruments, electronics. So you can do until we have reported this on up to 100 picoseconds. So you can switch this polar state up to down, up to 100 picoseconds. That's pretty fast. So that's a limit of the instruments. And of course, the device size, the RC constant is also limited by the device size. So if your device size you reduce a lot and resistance and capacitance product, you basically can switch faster. Yeah. So 100 picosecond is the limit that we have seen in our device size of like a micron size.
Okay, thank you very much.
Yeah.
So
Thank you.
with this talk, we end the session.